This is the example problem that we worked in class for finding the moment about a point due to a three-dimensional force. So we have a force of 500 pounds acting along the line from point A to point B, and we want to find the moment about the origin, point O. Well, we need to, we're going to take the vector cross product here. So let's write the force as a vector. We define the position vector from A to B. And to get from A to B, you can see that we'll be going in the negative x direction, 6 feet, in the positive y direction, 8 minus 2, or 6 feet, and in the positive z direction, or up, 5 feet. So that becomes our position vector, minus 6i plus 6j plus 5k in feet. Now we need to convert that into a unit vector, so we find the magnitude of this position vector, which is done simply by taking the square root of the sum of the squares of the components, and that comes out to about 9.85 feet. So that actually is the distance from A to B. The unit vector then that points in the direction from A to B is simply the position vector divided by its own magnitude. And of course the feet cancel out here, and so we're left with the dimensionless rather, unit vector. And so now to write this force as a vector, we simply multiply the magnitude of 500 pounds times the direction, that is the unit vector, and we come up with this for our force vector, minus 305i plus 305j plus 284k, and of course the units of that would be in pounds. Okay, we're going to take the cross product, but we also need the position vector from point O to some point on the line of action of our force vector. So point A seems like a reasonable choice, so we write the position vector from O to A, and to get from O to A we would come in the positive x direction, 6 feet, and over in the positive y direction, 2 feet. So that's our position vector. Now we could have just as easily used the vector from O to B, and we would have gotten the same final answer. So the position vector is from the point that we're interested in to any point on that on the force vector's line of action. Important here, we do not convert this into a unit vector. These distances are important because they are the moment arms. So now we're ready to do our cross product. The moment is r cross f, r being the position vector and f being the force. So we set up a 3x3 matrix, and we're going to find the determinant of that matrix. The unit vectors I, j, k make up the first row. The x, y, and z components of the position vector r make up the second row, and the x, y, and z components of the force vector f make up the third row. So to evaluate this determinant of this 3x3 matrix, we break it down by taking the top row. So for example, the top first position is I. Mark out the row and column that correspond to I, and now we have this determinant of this 2x2 matrix that's left times I. Okay. The next one for J, again mark out the row and column, and so we're left with the determinant of the 2x2 that's left here, but do remember you have to have a negative sign here, so be minus the determinant of that 2x2 times J. And finally for K, we mark out the first row and the last column and use this 2x2 matrix times K. And of course the whole thing will have units of foot-pounds because R is in feet and F is in pounds. So now we can evaluate these little 2x2s by cross-multiplying. So the first one, for example, we take the diagonal 2 times 253.8 minus the other diagonal 0 times 304.6, and that gives us 508. Same thing for the second one, gives us a value of 1520. And finally for the third one, we take the diagonal 6 times 304.6 and subtract 2 times negative 304.6, and that gives us a positive value of 2440. So plugging those in to our equation for the moment, we have our final answer, which is that the moment about point O, due to this 500-pound force, is 508I minus 1520J plus 2440K with units of foot-pounds. Now the other thing we get out of this is that we can find, of course, the magnitude of that moment turns out to be a total of 2,920 foot-pounds, but we can also find the distance from point O to the force, that is the perpendicular distance, because remember that the magnitude of a moment is the magnitude of the force times that perpendicular distance. So if we take the magnitude of the moment and divide by the magnitude of the force, we come out with the distance of 5.84 feet, which may be difficult to find otherwise in a 3D problem like this. Okay, we're going to look at the SolidWorks simulation or animation of this now. So we'll start out here now. Do ignore the X, Y, and Z components on here because we're used to using X out in this way, Y over here, and Z being up. So that's how I've laid this problem out, even though it doesn't correspond to SolidWorks trimetric definition. So here's point A, and here's point B, and so here's the line along which the force acts. Now, we can, from this, confirm that the length of this line is 9.849, which agrees with our calculations from earlier. And so from that, we're now able to show the force vector. Now, the scale of these has to be adjusted a little bit because remember that these vectors, the position vectors in feet, the force vectors in pounds, and the moment vector is going to be in foot-pounds. So the relative magnitudes of these are kind of unimportant. But here are the components of the force vector that we calculated. I divided them by 100 to make them fit better. So you can see in the x direction we're going in the negative x 304.6, in the positive y 304.6, and in the positive z 253.8 pounds. And again, we can confirm by taking the dimension of this line and see that it's 5 exactly, that the magnitude of the force is 500 pounds, and it's acting in the direction that was defined by A to B. Now we add the position vector here, and we can see we're coming forward 6 units and over 2 units here. So that is our position vector. Now the position vector and the force vector can be used to create a plane. And so we want we know that the moment should be perpendicular to this plane that contains both the point, which is the origin here, and the line of the force vector. So our last thing, let's go ahead and sketch in the moment. Again, we have to adjust our scale, and in this case we've had to divide things by 1,000 to make them fit nicely on here. But our moment, remember, was 508 in the positive x, so we're in front of the y-axis here by this distance 0.508. We go in the negative y direction, so this 1520, 1.520 is in this direction, and 2440 in the z direction. So that's the direction of the moment there. We can click on here and see that the magnitude of the moment, 2919, which we rounded off to 2920 foot-pounds earlier. And we can also, if we let's go ahead and close this for a moment. If I try to add a smart dimension here between the plane and the line here that represents the moment, you can see that it is 90 degrees. So remember that the direction of the moment is always going to be perpendicular to the plane containing the force and the point of interest. And finally, we can also show the distance, the perpendicular distance between the point and the force. And again, we found that rounded off to be 5.84 feet. So you can see it's confirmed here. And that would be a difficult distance to find otherwise, because of the fact that this is in 3 dimensions. And so you really have to get into the plane to be able to show that. So hopefully this helps a little bit with your visualization of what the moment looks like in 3 dimensions.